Hey, Basic Calc students, this is going to be your day 32 notes. We're looking at related rates today. Related rates are a super classic example of an application of derivatives. And we'll see why when we get into those situations in just a minute. Before we get there, though, there is a nice practice AP question that I'd like you to take a look at, given this function f of x. We have this extra little constant k at the ends. Tell me over which intervals the function f is increasing, on what intervals is the graph concave down. And then finally, we eventually get to address that value of k, find the values of k for which f has 11 as its relative minimum value. So I feel like it's definitely something we should feel pretty good at trying at this point based on all that we've talked about with first derivatives, second derivatives, curve sketching, things of that nature. You know, this should be one that's in our wheelhouse of like, yeah, we totally got this nailed. So try this, because when we come over to go over in class, I might just be putting up answers. We may not actually go through the full out solutions together. But let's get right into the good stuff. Talking about related rates on the next page. So as far as related rates go, a typical problem is that you're going to be given one rate, such as dx dt. Okay, so how the rate at which x is changing with respect to time. And then we're going to be asked to find another rate, such as dy dt, at a particular instant of time. So some good hints that we're going to use to help us figure out this, the answer to these questions is to draw a picture first and foremost. Sometimes you'll see the diagrams are given to you already, but if it helps to draw a picture, go ahead and do that. Step 2, determine an equation that models the situation. Step 3, differentiate with respect to t, right? Since this is all about relating to rates, we're finding the derivative with respect to t, which typically will involve some sort of chain rule step. And then we're going to make some substitutions after differentiating the known information and we're going to find the unknown rate. And this is kind of an important step. If we substitute too early some of the information, we won't in the end be able to answer the question as it's intended. As a quick aside, a good format to complete these problems is to state the given information, what we want, and when we want it to happen. So as you go through the examples with me in the notes, you'll see that this is kind of how I typically set it up so that I can break down nicely the given information and then be able to use that information to sub in once we've determined some equations and found some derivatives. So in example 1, it says the bottom of a ladder, 26 feet long, is sliding out from a wall at the rate of 4 feet per second. How fast is the ladder moving on the wall when the bottom of the ladder is 10 feet from the wall? Okay, so we're going to start by drawing a picture of this scenario. So we've got this ladder. Can I make the ladder really thin here? Ooh, that was really good. Okay, we've got our ladder. I'm impressed by that, guys. I don't know about you. Okay. And what do we know about this ladder? The ladder is 26 feet long. Well, that's never going to change, is it? As it slides out from the wall. This is why I don't get on ladders, by the way, because I don't want to be in this situation where the ladder is sliding out from the wall. Oh boy, sounds scary. And it's sliding out from the wall at a rate of 4 feet per second. So we're sliding this way. And that given information right there is the rate at which the x distance is changing with respect to time. So that's what dx dt is. Dx dt is 4 feet per second. What we want to find in the end is how fast is the ladder moving on the wall. Well, as it slides out this way, the ladder is going to be going down this way. When the bottom of the ladder is 10 feet from the wall. Okay, so if the rate at which the ladder moves to the right is dx dt, the rate at which it moves down the wall would then be defined as dy dt. All right, I've written a lot of the information off to the side of the picture, but let's set it up in the format that I described, where we're going to write the given information, what we want, and when we want it. Okay, well, the given information is we've got our ladder of length 26 feet. And we have the change in x with respect to t, which is 4 feet per second. So we know the length. We know the rate of change as the ladder moves to the right. What we want in the end is we want the rate that the ladder's moving down the wall. So we want dy dt. Specifically, we want that when the ladder is 10 feet from the wall. So we want that when x is equal to 10 feet. And based on all that, we now need an equation to represent the scenario here. Well, within this right triangle, where we have these three lengths that we're relating, sounds like a good old classic example to me of about a little old right? Pythagorean theorem. So I'm going to say x squared plus y squared equals L squared, where we have that L is the length of the ladder. Now, the only thing we have to be cautious about is what I mentioned up here in this step 4. Substitute after differentiating the known information, and then we'll find the unknown rate. The thing is that we can't sub in x equals 10 yet, and we don't want to plug in that 10 feet yet until we've taken the derivative, okay? Because that 10 feet happens after a certain period of time. So we want to take the derivative of this equation first. The one thing that I can plug in right now as a constant is the length of the ladder. Right? The ladder's not changing its length as it moves away from the wall there. So we're going to say that if x squared plus y squared equals 26 squared, let's take the derivative with respect to t. So that's going to wind up being 2x. And again, since it's respect to t, here's that chain rule step times dx dt plus 2y dy dt equals, well, the derivative of 26 squared, that constant is 0. Okay. So now that I have this, I get to just start plugging in some of the information that we know. So now I'm allowed to say, okay, that I found the derivative. We can plug in that x equals 10. So 2 times 10 is going to go there, times dx dt. The rate when x equals 10 is 4 feet per second. Plus 2 times y. Oh man, wait, hold on. We never even talked about what y equals. So we might come across some situations within our related rates where we get to something that is a hidden unknown. We maybe didn't realize or think in advance that we would need this value to sub in, and it's not directly told to us, but we have enough info to find it, right? So if the ladder is a length of 26, and we know that at this point x equals 10, we can do some quick Pythagorean theorem to find the value of y. And if you solve the Pythagorean theorem, you're going to get that because of the Pythagorean triple, right? This is a multiple of the 5, 12, 13 Pythagorean triple. We could probably very, very quickly in this case come up with the value of y to be 24. Okay, so we were a little nervous there, but you know what? We get to plug that in now. And then dy dt, that's what I'm looking for. That's what we want. Okay, so once you plug all that in, it's a pretty easy solve, isn't it? So 2 times 10 times 4 is 80, so that's going to get subtracted to the other side. 2 times 24 on this side is 48. So 48 dy dt equals negative 80. And when you divide the 48 over, negative 80 divided by 48 would reduce to, 16 goes into both, I think, right? So negative 5/3, and this is feet per second. Okay, done. Your first related rate in the books. So a couple things about this that are probably maybe slightly curious. Are we surprised that the rate at which it's moving down doesn't have to equal the rate at which it's moving to the right? So that's kind of weird, right? So the rate that we're moving to the right is 4 feet per second. The rate that it's moving down the wall is definitely not equal to, or the same as that rate. And that's going to change depending on, how far the ladder is away from the wall at a given time. So this would change depending on that scenario. And then in addition to all that, we shouldn't be too surprised that this answer is negative because we're moving down at that specific rate. So when we get our final answers, just thinking about, does our answer make sense? Certainly we'd want the answer in this case because of the rate and the value that we're moving down along the y-axis there to be a rate that's negative. So negative 5/3 feet per second is the correct answer. Okay, a little bit more with related rates. We're going to take a look at example 2. So this is an example that we're looking at an oil spill from a ruptured tanker. And it spreads in a circular pattern whose radius increases at a rate of 2 feet per second. So we're given a rate. It's the rate that the radius is increasing. How fast is the area of the spill increasing when the radius of the spill is 600 feet? I don't think we necessarily need a picture for this one. I think the picture, even in the last case, I think it does help, even though it's a simple right triangle scenario. This one's just an area of a circle that's spreading as time goes on. So if you want to draw a picture of that, go for it. I'm going to get right into the given, want, when. All right, the 3 things that I think help us to set up these related rates. So what are we given? We are given the rate at which the radius is increasing. So we're given that dr dt is equal to 2 feet per second. What we want in the end is how fast the area is increasing. So we want to figure out the rate that the area is increasing with respect to time. So we want dA dt, specifically when the radius of the spill is 600 feet. Okay. So what's the formula for an area of a circle? Cherry pie is delicious. Apple pies are too. That's pretty easy. Okay. You can see why we really can't plug in that value of 600 right away, right? We have to take the derivative first. Because if you plug in 600 first and then find the derivative, you're finding the derivative of a constant. So you would find at that point that, the derivative dA dt is equal to 0, which doesn't make any sense. So in this scenario, let's find the derivative first. After we find the derivative, then we'll plug in some of the information. So dA dt in this case would be 2 pi r dr dt. Okay, so again, just don't forget that sort of chain rule step that we're taking the derivative of r with respect to time. And then, guys, it's really as easy as just substituting in the given values. We are given that the dr dt is 2 feet per second, and we want to know what's happening when the radius is 600. So if you simply plug those 2 pieces of information in, we get that multiplying all this out, we give you that the area is changing at a rate of 2400 pi, and this would be because it was in feet squared per second. Okay. Okay. This last one is really similar to this one up here. We're talking about area changing with respect to time. So for the last one, even though we're somewhat new to related rates, I think you can try it. We'll go over this in class with number 1 as well. But instead of dealing with an area that's changing over time, now it's a volume that's changing over time. And it's the volume of a sphere, which is given to you there. So go ahead and try this one. I promise you we'll go over it next time I see you. And we've got a lot more related rates in your future. So have a great rest of your day.